Okay, so a little bit of smaller class today, but hopefully we can turn that into some more physics learning. And, we always have the recording for people who can't come. So we're going to pick back up where we left off on oscillations. But before I do, a quick note or a quick couple of notes. So there's a second part to the video on entropy and osmosis. Thank you to the people who alerted me to the fact that the last quarter of the video, the audio was completely corrupted. And so I re-recorded it and it should be available on the Pages tab now. And then I think I've finally fixed the homework issue of deducting points, but it was a little bit weird. So hopefully that that works now. If it hasn't, please do just let me know and I'll go back into the settings on Pearson and see if I can get it finally figured out. Okay, so just to refresh you from where we were yesterday. So far we've been thinking about simple harmonic motion, which is a special case of periodic motion where the position versus time of the object can be described by a sinusoid. So a sine or a cosine, or potentially one of those with some phase, so shifting it to the left or right. And we were just learning about how to apply initial conditions, so how we start off the oscillation in order to calculate the phase of the system. And we had this example here of trying to identify which of these 4 spring mass systems has a phase constant of pi/4 radians if this picture is of them at a time of 0 seconds. So this is these images are the initial conditions. They show where this mass is located at time 0, and they tell us which direction it's moved. And those 2 pieces of information are enough to find the phase for one of these spring mass systems. So what I wanted to, oh, I forgot to enable the annotate. Sorry, 1 second here. There we go. Okay. So one of the things that I mentioned to a student after class, but I thought would be good to share with everyone, is that if you think about the 4 quadrants on an XY plane, we can start to imagine where in each of these quadrants is the sine function positive and where is the cosine function positive. And this can help us in determining which initial condition is the right one for the phase pi/4. And so what we see is that, what we've been using is that at time 0, our x position is a cosine of phi. And then if we look at the velocity function for that position relationship, then we'll get negative Vmax sine phi for the velocity. So these are, if you don't remember anything else about initial conditions, if you just have these 2 formulas, that's really all you need. And so what we can say is that cosine is going to be positive. So cosine is positive in quadrants 1 and 4. And then sine is positive in quadrants 1 and 2, but this is negative sine. So it will be, this negative sign will be positive here in quadrant 3 and positive here in quadrant 4. And so what we see here is that we have an angle phi or pi/4. So that will be in quadrant 1. Positive pi/4 is in quadrant 1. That's a 45-degree angle. And so we expect that the position is positive. So we can cancel out these 2, right? Because the position is described by cosine of phi, and cosine of something in quadrant 1 is positive. So we expect our mass to be to the right of the 0 location, the equilibrium. And then additionally, so negative sign is positive only in quadrants 3 and 4. So negative sign is actually negative here. So this is the correct answer. So this would be our mass with a face of pi over 4. So you can think about where these functions are positive and negative based on the 4 quadrants of the xy plane, and let that give you a hint about where we expect the phase to be based on our initial conditions. And this can be really helpful when you're trying to narrow down, what angle you're supposed to have in your equation, or if you're working backwards like we are here, and we're trying to figure out which image matches our phase. So it's a way to check yourself. Are there any questions about this method of using the quadrants to think about the plus and minus sign of position and of velocity? Okay, very good, very good. So then I know there's a lot of stuff on this slide, but this is more for your reference later. So I actually typeset this myself because I couldn't find anything that matched what I wanted you to have. I don't know why this screen share thing is in the way. And now everything's frozen. Okay, well, having some technical difficulties. I'm just going to do this. There we go. Okay, sorry about that. Difficulty there. So I typeset these to give you a helping hand when you're trying to solve the inverse trig functions here. So you'll have to do that in 2 situations. So one situation is what we saw yesterday at the end of class with finding the phase. So when you're trying to find phi, you'll have to, set your initial position equal to a cosine phi, because that omega t at time 0 will go away. And so to actually find phi, you're going to have the inverse cosine of x initial over the amplitude. So this is one case where you'll want to solve for the inverse. But additionally, what I could ask you, and what I think is going to be a fair question, so I encourage you to practice it, is if I tell you a position and I ask you at what time does the mass sit at that position? Okay. And there will be an infinite number of times, right? Because these are periodic functions. So there will be an infinite number of times where the mass is at any given position. And it'll be your job to tell me some formula for all infinity of those times. But it's important to note that there are 2 types of solution. So going back to this slide, in options C and D, the mass is at position 71. So if I asked you, at what time is the mass at position 71? You could tell me whatever time it's at this picture C, or whatever time it's at this picture D. But you can see that those are fundamentally different solutions. One is moving to the right and the other is moving to the left. So we're going to have to think about not only at what time is the object at that position, but is it moving to the right or to the left at that moment in time? This is an important question. And so I walk you through the steps here, but just to spell them out. So we start off with our position function, and I'm just taking the phase to be 0 here, but hopefully it won't be too hard if I asked you to also have a phase. You could just kind of tag it along, you know, omega t plus phi, and then eventually you would have to subtract it when you're solving for t. But anyways, so you get everything on the other side, take the inverse cosine, divide by omega, and you get this line, which is one of the time solutions. I call it T1, but that's not going to necessarily be the first time that this happens. And when you plug this into your calculator, you will get some number here. And this is where the graph in the middle comes into play. So you can see this blue dashed line. This is the inverse cosine, sometimes called arc cosine function. And the range, so the outputs that it can give you are only positive numbers, so from 0 to pi. So if I give it any ratio, the inverse cosine is going to give me some angle, but it can only output angles between 0 and pi because it's a periodic function. So if it had a larger range, then it wouldn't know which value to tell you. It would be no longer a function. It wouldn't pass the vertical line test. And so what you have to realize is that the value for the time that your calculator gives you when you plug in inverse cosine will be some positive value, so some positive angle between 0 and pi, and then it's going to be scaled by this 1 over omega. And if you want to find, so that'll be one of your types of solutions. So you can immediately come down here and you can write that whatever time your calculator tells you plus 2 pi n over omega. So all of the that takes account for the periodicity of the function. So you'll have the first time it's at that position moving, let's say, to the right, and then if you add 2 pi over omega, that'll give you the second time that it's at that position moving to the right. If you add 2 pi over omega again, that'll give you the next time it's at that position moving in the same direction. But if we want the solutions where it's at that same position, but moving in the opposite direction, then we have to do a little bit of trickery. And we just say that at the negative of what your calculator gives you, you would also have a valid solution. And the reason for this is that cosine is an even function. So whatever it looks like to the right, it looks the same to the left. And so if we find that, let's say we're interested in what time the function is at this position. So we would get our T1 here, and that's what our calculator would tell us. And then if we go to negative T1, that would be our T2 here. And then what we could do is we could see that if we go over by 2 pi over omega, we'll get to the next value. Or if we went 2 pi over omega the other way, we would get the other value. And that for each of these, the slope is down. But that alternatively, we could take this position T2 and go 2 pi over omega, we'll get this dot. Or we could go this way, 2 pi over omega, we get this dot. And all of these, the slope is up. So for this graph, the T1 and all of its compatriots would be at that position moving to the left because we have a negative slope, whereas T2 and all of its fellows separated by 2 pi n over omega would be at that position but moving to the right because it has a positive slope. And so if I asked you at what time, like all the infinite times, is this mass at this position, this is the answer I would want you to give me. But of course, plugged in for T1 and T2. So T1 and T2 would each be some number, some angle. And then, and we're assuming they're in radians here, if we're using 2 pi n over omega as the thing to take into account the periodicity. And then you would just have to plug in your omega, and then you would leave n just as a variable. That's just some random integer because there are an infinite number of possible solutions that are all just separated by this factor of 2 pi over omega. Okay, so that's solving for cosine, which is, and I would really recommend that you would just use cosine for position as often as you can. Sometimes if you have a phase of, pi over 2 or minus pi over 2, it'll be easier to just use sine for your position. That's equivalent to the physical condition of you have your mass on a spring and you flick it. That's your initial condition. So if that's what's happening in the system, I can't blame you for using sine. It definitely will be easier in a sense. But you can see that when you use sine, everything works the same way, except to get T2, it's a different formula. It's pi over omega minus T1. And that's because the sine function, so sine is not an even function. It's an odd function. And so if we find a solution here, we can't just go to the other side and expect to see a solution over here, because that's not where the sine is. So what we have to do instead is we have to go over by pi, and then whatever this distance is, T1, we have to go backwards by that to get our second solution. So that's where this formula comes from. And anytime we're dealing with time and we're trying to think about shifting it in terms of angle space, we need to make sure to divide the angles by omega, which is going to scale them based on the frequency of our system. Right, omega is the angular frequency, so it acts as a conversion basically between angles and time. Omega is an amount of radians per second, so it's our conversion factor. So be careful. I actually, if you have the earlier version of this slide, I caught my mistake of not putting in the omegas, so you might need to put them in yourself by hand if you're taking notes on it. But anyway, so this is the trig interlude. And you can see that actually arc sine has a range from negative pi over 2 to pi over 2. So your calculator, if you do an inverse sine, might give you a positive or a negative answer. And so if you get a negative value for T1, then when you find T2, you'll have pi over omega minus a negative number. It'll end up being like addition. So this formula is consistent with that, if you were worried. And so the thing to watch out for is that often we'll ask for like the third time this is in some position. And if we do, you'll just have to either write out in a table or look at a graph that you could draw or use your calculator to produce and figure out what values of n you would need to get each of these solutions, moving up, up, up. So for example, in this image up here, so looking back up on the top left, if I asked you for the third time that the mass on a spring passed through this point of interest, it would be this one, right? Which confusingly, so this is T1 plus 2 pi over omega. However, if I asked you for the second time, it would be this one, which is, so remember our T2 is actually negative, so that's not a physical solution, but that second time that we pass through this point would be T2 plus 2 pi over omega. So this is just the point where I have to add that technically the negative time values in a system like this, if we consider the start to be at t equals 0, those negative time values aren't actually physically real. They're not describing the system because we just flicked it or pulled it back at time 0. So before that time, our simple equations, sines and cosines, don't actually describe what the mass was doing. Maybe it was just sitting there forever. So, maybe the reality is that it was sitting at position 0 forever until we pulled it back and then it started oscillating, right? That's one possibility. So basically, if you're thinking about these times before the start of the experiment, whatever your functions tell you, those aren't real solutions, but we can shift them over by factors of 2 pi over omega to get to the part of the function that actually is describing the physics of a real mass. So if this is confusing, come back and rewatch this part in the recording. There are videos online about it, but for whatever reason, I don't know, they just don't want to give you these formulas for T2, which really annoys me. They just want you to kind of intuit it from the unit circle a lot of the time. But we're going to be dealing with cases where the inverse cosine doesn't just give you a nice number. It'll just give you some random, messy, irrational decimal thing. And so you just need to be able to say whatever I get from my calculator, I just slap a negative sign on it if it's cosine, or I do pi over omega minus that if it's sine. And that's how I get the other type of solution. And it won't be obvious from your calculator which solution is which. So which one is telling you it's at that position moving to the right, and which one is telling you I'm at that position moving to the left. So to get that information, you either need to draw the graph or you need to plug into the velocity equation. So if you plug in that time to the velocity equation, you can see if you get a positive or a negative number. So, but once you find out, like if you find one of these T1 solutions is a positive velocity, then all of those separated by 2 pi n over omega will be positive velocity. They're all going to be the same type. So like all of these will be in one direction and all of these will be in the other direction, but at that same location. Okay, so lots of math here, but like I said, expect to see these types of problems in your future. So I don't know if that'll be on the quiz tomorrow or probably that's too soon, but at least on the homework and maybe sometime in the future. Okay, any questions about this while we're here? Good, good. So now we're going to move on to the next section, 15.3, which is looking at the energy in a simple harmonic oscillator or a system in simple harmonic motion. So there are only two types of energy, at least in the frictionless case. We have kinetic energy and we have potential energy. And so our kinetic energy is just this 1/2 mv squared. And our potential energy has a very nice, very similar looking equation for a spring. It's 1/2 kx squared. And so hopefully you saw maybe a little bit of this in 3a, but if we have a force like Hooke's law, negative kx, then if we do the negative integral of it, we get 1/2 kx squared. So force and potential energy are related by a negative integral because that's related to the definition of work, right? Work is integral f dx. If you have a changing force, you can't just do f dot x. You have to actually care about that, the fact that there's a x variable in the force law. And so that's why we get a 1/2 kx squared. But anyways, you don't need to know how to derive it. You just need to remember that that's what the energy is. And the most useful part of this, so the reason I even bothered to make some slides about the energy section that I personally think is otherwise kind of boring, is that we can imagine what happens when our system has only kinetic energy. So if the mass is oscillating back and forth, there'll be a brief moment where it's passing through the middle. And at that point, where it's passing through the middle, it doesn't have any potential energy in the spring, right? Because the spring, there's some length of the spring where the spring is happy. That's its equilibrium position. We usually call that position 0. And so if we have our mass oscillating, whenever it passes through that equilibrium point, the spring is happy, so it's not storing any energy. It's its lowest energy state. And so at that point, we only have kinetic energy, and that's where our mass will be going the fastest as it passes through the center. Now it'll do that in two different directions, right? To the left or to the right. But our energy equation doesn't care about the direction of the velocity. Kinetic energy just is a scalar quantity. It can only be positive. So this left side is when all of our energy is in the form of kinetic energy. And you can see that happens. So this graph is a little bit confusing, but at the 0 point, this green curve is the kinetic energy. So this is the kinetic energy, and then this blue curve is the potential energy, which we usually give the letter U to. I guess they're labeled on the right side here. So you can see at the origin, we have only kinetic energy, 1/2 Vmax squared, and no potential energy. But we could also look at the amplitude points. So this, we call them turning points, where the mass turns around. And at those positions, we only have potential energy, 1/2 K A squared. Okay, so for a brief moment, the mass stops moving. It was moving to the right, and it ends up moving to the left. So by the intermediate value theorem, it has to be 0 at some point. And the only natural asymmetrical point for that to happen is at the amplitude itself. And so we get this relationship that the maximum kinetic energy has to be equal to the maximum potential energy because energy is conserved. So we could, we have two buckets, one labeled kinetic, one labeled potential. We can slosh the energy back and forth between them. At most points, it's going to be a combination of the two. But if we think about how much fluid we have in the one kinetic at maximum versus how much we have in the potential at maximum, that has to be the same. And this at first looks like it's a useless relationship, but remember, we have an equation for Vmax. We've already found that Vmax is 2 pi f a, or alternatively, we can write that as omega times a. And this is where we get our next and really our final critical piece of information about the position equation of an oscillating system. So we plug this in, 1/2 m omega a squared equals 1/2 k a squared. And we can get rid of these 1/2s. And then we're going to square both of these things. And we can get rid of the a squareds as well. And now we're able to write down a formula for omega. We can say omega, the angular frequency, is the square root of k, which is the spring constant, how stiff is the spring, over the mass on the end of the spring, m. And it's a really beautiful result. What this tells us is that it doesn't matter how far out we pull the spring. I mean, of course, in a real system, if you pull it far enough, you'll break it. So we can't pull it infinitely far. But for a big size spring, you can pull it any reasonable distance, whether that's very tiny or huge, and it will oscillate at the same frequency, right? This angular frequency is just proportional by a factor of 2 pi to the actual frequency f. So no matter how, you see that this formula for omega doesn't have how far did I pull it. It doesn't have an amplitude in it. It only has the stiffness of the spring, which is a natural property based on how we make the spring and what we make it out of, and the mass that's on the end of it. So those two things alone are enough to determine how quickly our system oscillates. And we'll see that there's a very similar relationship for a pendulum. And so for a pendulum, it doesn't matter how far we pull it and let it go, as long as it's small enough, due to some reasons we'll talk about. But within some range of angles from 0 to 15 degrees, we can pull it back to any of those, and the pendulum will have the same frequency. And that's why pendulum-based clocks were so popular, because it doesn't matter how we start the pendulum moving, as long as we continue to give it some energy, which is a topic that we'll also cover called driven oscillation, then it'll continue to tick at the same rate. And if we craft that pendulum carefully, we can get it to tick at a rate of 1 oscillation per second. And so that's how we can keep track of time. And very similarly, these oscillations can keep track of time by tuning their frequency to be, either once per second or a set number of times per second, and then we just adjust the output. And that may sound like something that we don't do anymore. Many people don't have mechanical watches unless you're like a watch aficionado. But modern watches use quartz-based resonant systems that actually do still vibrate. It's just a crystal lattice vibrating, but it follows the same formulas. So something like the stiffness of the atomic bonds over the mass of the atoms in the lattice, if you take the square root of that ratio, gives you the angular frequency of that oscillating quartz system. So it's a very similar idea. Okay, so I pulled this from the book just to have all of the formulas down for you. So the one I would recommend you remember is this leftmost one. So I recommend you remember this one. And then to get the other two, you should just know that omega is 2 pi f, and that the period is 1 over the frequency. So these are the formulas you should actually know. But for the case of a spring, you can plug in that omega for each of these and get the frequency and the period in terms of the mass of the system and the springiness, the spring constant of the system. And so when you're given problems in the future, so the examples we had yesterday, they would tell you something like the mass oscillates 15 times in 10 seconds, right? And that let us get the period and the frequency, and then we could get the angular frequency as well. But in the future, you may be given problems where they just say, here's a 100-gram mass on a spring with a spring constant of 50 newtons per meter, calculate the frequency or the period. And you just have to plug in the mass and the spring constant. Just be careful about the units, right? We want the spring constant has units of newtons per meter, and the mass has units of kilograms. And if you do that, then you'll get angular frequencies with units of, radians per second. So just use the standard SI units, basically. If you're wondering where I got newtons per meter, that just comes from thinking about Hooke's law. If we know that F equals negative kx, x has units of position, force has units of newtons, so K has to have units of newtons per meter. So if you're confused about units in a problem, look at your formula sheet and find a formula with the thing that you're interested in, and then think about the units you would need it to have in order for the formula to work out. That's a good tip. Okay, so let's do an example problem. So in the figure to the right, the 4 springs have been compressed from their equilibrium positions at x equals 0. When released, the attached mass will start to oscillate. So this is like right before we release them, these are their positions. Rank in order from highest to lowest the maximum speeds of the masses. Okay, so remember the maximum speed, V max, is A times omega. And what was omega for a spring? Okay, good. So root K over M. And so now we just have to basically evaluate this for each of these systems. So they tell us the spring constant. They're all spring constant K except option B. But let's just go through and quickly, I'm not going to write V max, I'm just going to write V. But let's write these down for each. So for the first one, we've moved it back by 10. And we have a spring constant K and a mass of 4m. So we can just leave it like that for now, and we can come back and compare them. The next one, we have 20 times root K over 2, and then times 4m. So we could just write this as K over 8m. The next one, we have 20 times root K over 2m. And the last one, we have 5 times root K over m. Okay, so now in order to evaluate this, we can try to simplify it as best we can. So we can take out the square root of 4. This gives us 5 over root K over 5 times root K over m. This one won't work out quite so nicely, but we could at least make this 10 root K over m, over root 2. Again, not quite so nice, but 20 over root 2 root K over m. And lastly, we have 5 times root K over m. And so now they're all in terms of root K over m. So if we want to compare them, we can just compare the coefficients. And so which one of these is the biggest? Which has the biggest coefficient here? Right, so it's this one. Root 2 is like what, 1.4 or something like that. 1 point, I don't know. I don't remember what it is, but I know it's between 1 and 2. So that's all that really matters here. So just take it to be 1.5 or something. So 20 over 1.5 is going to be bigger than any of these others. And then this would be second, and then these two are equivalent. So they're tied for third. Very good. Okay. Any questions about how we would solve this problem, right? It's basically just using our new information that omega is root K over m, along with that maximum velocity formula, and then plugging in for each of the systems and realizing that if they all share some variables in common, and we're just trying to compare them, we can ignore those variables they share in common. It's a very common trick in physics to just compare things without actually knowing what they are, just how they relate to each other. Okay, so I just wanted to also give you this example similar to what we were talking about with quartz of how atomic and molecular systems, in general, they have complex potential energy functions. So you can see here that this blue curve is the potential energy function of some molecular system. And if it were actually simple harmonic motion, then this potential energy curve would have to be, related to a parabola. It would have to go like x squared, something, 1/2 kx squared. And you can see that this curve clearly is not a parabola, right? It's got some weird horizontal asymptote on the right side, and it's blowing up on the left side. But what we can do is we can just zoom in to this bottom region. And for any function with a minima, that if you zoom in close enough, it'll start to look like a quadratic. So for small oscillations, atomic and molecular bonds act like masses on a spring. So if you have a bunch of molecules attached to each other and you give them some energy, maybe you heat them up to get them to start vibrating, maybe you smack them really hard with some, with your fist or something else, then those vibrations will be, some happening at some frequency that we can approximate at least as just being like a mass on a spring, so root k over m. And we oftentimes know the masses of these, atomic or molecular objects, but the thing that the frequency lets us figure out is k, the stiffness of these springs, which is related to the bond strength. So the bond between the molecules has some springiness to it, and by making these molecules or atoms get excited by giving them energy, they start to oscillate, and we can measure the frequency of that oscillation, and it tells something about the bonds between them. So this is a really useful tool in physical chemistry to measure properties of different substances, and then we can use that to predict how they will behave under different conditions, or even to predict how like the enthalpy of the bonds might behave. There are lots of things that we can do just by getting this k value effectively for some molecular system. So just something to be aware of in case you see it in your future. Of course, the energies involved, like you can see, are very small. So order 10 to the minus 19 joules. In physics, we call those energies order electron volts. And that's kind of the energy that you should expect to see in atomic and molecular systems, because if you think about how much energy it takes to ionize a hydrogen atom, that's 13.6 electron volts, which is around this energy scale, 10 to the minus 19 joules. So, okay, so then moving on to chapter 15.4 or section 15.4. This is a very busy diagram, but it's attempting to show you the forces involved at each position. And correspondingly, the acceleration, right? So we know from 3a that force is just mass times acceleration. And for these mass spring systems, the only force is coming from the spring. So this is just negative kx equals ma. But of course, a is, the second derivative of position. So this is a differential equation. We have a variable having its derivative taken, set equal or proportional to that same variable. So there's a whole course in the math department, or many classes actually, about how to solve these. They're very important in engineering and the sciences. I won't make you solve this, but if you do, then you just get our old friend, actually. You just get a cosine omega t plus phi. So we've already seen the solution to this differential equation. So if you're wondering where that comes from, it really just comes from F equals ma. But what I want you to understand from this section is mostly just looking at the acceleration. So as we stretch this spring out, or as we compress it, we're making the force larger. So therefore the acceleration is getting larger. Okay, so by the time you're at the turnaround point, where the velocity goes from one direction to the other, and your mass spring goes from compressing to expanding, for example, your acceleration there is really, really big. which is confusing for people because your velocity at that point goes to 0. But the origin of this, do I have a picture? I guess not. The origin of this is that if your position function looks like a cosine, so if this is your x, when we take the derivative, your velocity function will look like a negative sign. And your acceleration function then will look like a negative cosine. And so whenever the velocity is 0, like here, that's where your acceleration is at its maximum. Okay, and so what you should remember from this image is just that the acceleration for a mass spring system is biggest when the position is at an amplitude or a minus amplitude. So when it's at one of these turnaround points, either the farthest it gets to the right or the farthest it gets to the left, it has a 0 velocity momentarily, but its acceleration will be maximum. Okay, and to get the value of that acceleration, instead of omega times a, it's just omega squared times a. If you think about the chain rule, if you're familiar with derivatives, it's just because we get another factor of omega coming out of that trig function, basically. So just to remind you, Vmax was omega times a. And so we can do a sample problem with this. So here we have the John Hancock Center in Chicago. It's 100 stories tall. And strong winds can cause this building to sway back and forth. So the potential energy function there probably looks obscenely complex. But we don't have to worry about that potential energy function too much if we can just think of the system as undergoing simple harmonic motion, which will be approximately true as long as it's just not oscillating by very big of an angle. And if the building is well designed, hopefully it's not oscillating by very much. So it'll be a good approximation. Okay, so then they tell us on some windy days, the top oscillates with an amplitude of 40 centimeters. So our amplitude is, let's say, 0.4 meters. And a period of 7.7 seconds. So our period is 7.7. What is the maximum acceleration at the top of the building? And so that sounds like a really hard question if it weren't for the fact that we have a nice, very simple formula for the max acceleration that just comes from, our derivatives of the position function. And so they already give us the amplitude. All we have to do is to convert this period into an angular frequency. So the first thing I would recommend is to convert it into a regular frequency by just taking the inverse. So if you do this, you should get about 1/10 of a hertz. And then what we can do is further modify our frequency by multiplying it by 2 pi. So now instead of cycles per second, we're talking about radians per second, right? There are 2 pi radians in a cycle, so we should multiply by 2 pi. If you get confused, just put in the cycles and the radians and things and look at your units and do dimensional analysis very carefully. And you can always get formulas like this yourself. And so when we plug that in, I get 0.82 radians per second. And so we're almost done. We just have to plug our amplitude and our omega into this A max formula. And I get 0.27 meters per second squared. Which is, a very small number. So remember that G, the free fall acceleration, is 9.8 meters per second squared. So this is like 3% of that, 4% of that. So comparatively very small, which is what we would hope. We would hope that the top of our building isn't accelerating very much, even though it's moving quite a bit, right? 40 centimeters is quite a bit of motion. You would definitely feel that if you were standing at the top of that building, but the acceleration pretty small. So we don't have to be too concerned in these conditions about the building collapsing or something. Okay. So now we'll move on to section 15.5, which is looking at a very, very similar type of physical system, which is the pendulum. So what we're going to see is that all of the equations, all of the apparatus that we've been learning for a mass on a spring is also true for a mass on a pendulum. But we're just, instead of talking about position, we're going to be talking about angles. So it makes it seem a little bit more complicated, but it's exactly the same math. All the formulas are shared. So it's really the same physical system from a mathematical standpoint. But we're about halfway through the class, so I'll give you your 5 minutes and we can stretch and talk a little bit and get our brains back to focus. Yep. Your slides? Yeah. So this one? Yeah. Okay. You want to stare into the mess of arrows.
Mechanic,
Mhm.
you said that the velocity was largest at the position turning points.
At the turning points, the velocity is 0.
Oh,
So the velocity is largest when it goes back through that center, the equilibrium point. But the acceleration is largest at the turning points. Yeah.
oh,
Yeah. So it's tricky. The position, velocity, and acceleration functions are all sinusoids, but they're shifted from one another. So they have different phases.
so that means if acceleration is biggest when the position is at the turning points. That means acceleration is biggest when velocity is at 0.
Correct. Correct. Yeah. So it's weird, but you can have any sort of relationship between velocity and acceleration in terms of value, as long as acceleration is the derivative of velocity. But you can see in the function here. So at the time 0, so that leftmost point that I drew in these sinusoids up here, that this is when the mass is at its maximum. So it's at the rightward maximum position. The spring is fully stretched out. At that point, it's not moving, velocity is 0, but it does have its biggest acceleration, because the farther you stretch it out, the bigger the force is. And the bigger the force is from F equals ma, the bigger the acceleration is. So that's kind of the idea. So it takes a bit, so think on it. But that's the physics. Okay, so should probably hop back into this. Hopefully we can finish up this section today, but I've been trying to do more examples. Hopefully that's been helpful, but it is slowing us down a little bit. But anyways, so the pendulum, if you're unfamiliar, is just this idea in physics of having some sort of weight, so a mass on the end of a string. And for the simplest case, you have to think of the string as being very thin so that we can ignore its weight. So if you just have a very thin, any sort of normal string you would encounter, like a shoelace or something, would be a totally valid case to take its weight to be basically zero. If you stick like a chunk of iron or wood or something on the bottom. And so sometimes we call the mass on the end of a pendulum a bob. So just be aware of that terminology. But anyways, what we typically will do then is pull this mass back to some starting angle. And that would be our amplitude, the largest angle that we pull it back to. And then we let it go and it'll swing back and forth, right, left and right. But if we hadn't ever pulled that mass back, it would be happy to sit at the zero position. So the zero position where the pendulum hangs straight down is like the equilibrium position for a spring, where the spring is at the length that it likes to exist at. And what you can see is the reason that the pendulum swings back and forth is that our tension has a direction up the string, but the weight, as always, is pulling directly downward. So what we need to do is we need to think about the fact that part of the weight goes to cancel the tension, so that's not going to cause it to swing. But this part of the weight, which is perpendicular to the tension, is an unbalanced force. And so that part of the weight, which is just the mg sine theta part, is what actually causes the pendulum to move. And if you think about the graph of sine, when you're near the origin, near zero, the graph of sine looks a lot like the function y equals x. And this isn't just something that you can say approximately, you can actually prove, if you look at the Taylor expansion, that this is really true. And so what we can do is we can say that this force, as long as the angle is small, is approximately mg theta, for theta in radians. And so it'll be pointing in the direction opposite that where you've pulled the mass to. So at the end of the day, we can write down a restoring force, negative mg theta, which looks really similar to Hooke's law, negative kx. And you can see here that this mg is replacing this k, and that this theta is replacing this x. Okay. And so when you plug this in, what you'll find is that we can derive our omega, and I'm not going to do it for you here for the sake of time, but it's done in the book. We find that omega is root g over L. So there's going to be an mg in the numerator that'll cancel the m in the denominator that we saw in the spring case. And then the factor of L comes from the amplitude, basically, of the system when we pull it back. Or alternatively, you can imagine that it comes from needing some conversion between angle and length. So we need some L factor. So in any case, all of the other formulas, then we can just use this omega we get for our pendulum and find the frequency and the period just as easily. And then we can write things like theta of t equals our amplitude times cosine of omega t plus phi, right? So this would be our general solution for a pendulum, where theta naught, this is just the maximum angle that you pull this to. And then phi, this is our phase. So we would have to solve it from our initial conditions, just like in the case of the spring. And then our omega is going to be based on, G, which is basically what planet am I standing on, and L, which is how long the pendulum is. So it's a really beautiful formula. And like I said, this is what allowed humans to first tell time in a very consistent way. And critically, because if you imagine going around the world, if you set your clock for like London time, and then you traveled westward to America, and you looked at when the sun was directly above you, what time does my clock say? Your London time clock wouldn't say noon, although you could expect the local time would have noon be when the sun is directly above you. And so that difference in time actually tells you how far west you've traveled. So this is the idea of, longitude. So if you want to measure your longitude, you actually require a very accurate clock. So there's no way to measure longitude around the Earth without a good clock. You can measure latitude because the Earth is spinning around its axis, and so you can look at the relative position of stars and measure latitude. But longitude was really tricky, and a lot of sailors, including Columbus, had some very tricky difficulties due to the difficulty of measuring longitude. And so there was actually a huge prize of like millions of dollars offered back in, I want to say, the 18th or 19th century, if someone could devise a good way to measure longitude, and it ended up being basically by using a pendulum-based clock. So important part of history. So anyways, let's calculate this something related to this pendulum clock. So if we have a grandfather clock, like shown in this image, designed so that the swing of the pendulum from one side to the other takes 1 second. So be careful with that. That tells us that the period is 2 seconds, right? Because the period is how long it takes to get from one side to the other and then back. Okay. So a period of 2 seconds. What is the length of the pendulum? And then what is the maximum speed of the pendulum bob? So remember, bob just means the mass on the end if the pendulum swings to an angle of 8 degrees. Okay, so the first question is just a great example of our using our formula omega is root g over L. So we can plug that in and just use the period version. So the period is 2 pi root L over G. And now we can rearrange that for the length. So the length is, we can divide both sides by 2 pi, square it, and then move the G over. So we get G times T over 2 pi squared. And by plugging in 9.8 for G, 2 seconds for T, we get, let me see, 0.993 meters, which is a really important length. This is the actual length that most grandfather clock pendulum systems are tuned to be at. So that's why they're this size, basically. And then what is the maximum speed of the bob if the pendulum swings to an angle of 8 degrees? So we can just use our same Vmax equation. 1 second here. And it'll just be the amplitude 8 degrees times our omega, which is just 2 pi, let me be more careful with this. I'm reading my notes. So our maximum angle is 8 degrees, but in order to use this equation, Vmax equals A omega, our omega is in units of radians per second. So we need to convert this amplitude into radians as well in order to have a consistent set of units. Okay. So first what we want to do is 8 degrees times 2 pi radians over 360 degrees. And that's not our Vmax, that's just going to get us our A. And when I do that, I get 0.14 radians. This gets us our, bungling this a little bit, this gets us our theta naught, 0.14 radians. So if we wanted to write theta of t equals theta naught cosine omega t, this is the value we would use for theta naught. But to get A such that this formula works out nicely, we have to use the equation R r times theta. And the r here is just the length of the pendulum. So our A is L times theta naught. We have our L, we have our theta naught. So this is 0.139 meters. And now we can finally plug in. Sorry, I'm skipping some important steps here. So we plug in our A of 0.139 meters. We plug in our omega, which is just root G over L. Since we know L, we can now get that. And we get 0.437 meters per second. So if we wanted just our, so we could use the formula omega max, which is very confusing, but here this is angular velocity. And this is actually the derivative of our theta of t. And so this would be theta naught times omega, where this is our angular frequency. So there's a reason that people who aren't physicists don't tend to use this formula, because it looks terrible. There are two different things, both represented by omega in it. But if you're using the standard Vmax formula, we want to get a velocity in meters per second. So we need our amplitude to be in meters. So whatever angle we have in radians, we need to convert that into a arc length in meters by multiplying by the radius. And for a pendulum, the radius is just the length of the pendulum. Okay, so I did that in a rather roundabout and unpolished way. Are there any questions or need of clarification on how we solve this problem? So just to walk us through again, we can use the angular frequency formula to find the length of the pendulum. And then they tell us that we swing to a maximum angle of 8 degrees. If we want to get our theta naught, our amplitude in angle space, we have to convert that to radians. And then if we want to get our amplitude in terms of arc length, so in terms of meters, we need to multiply that by the length of the pendulum. Because an angle in radians tells us how many radius lengths the arc is. And if we multiply by how many meters the radius is, we'll get the actual arc length in meters. And then if we take that arc length in meters times the angular frequency, we'll get our maximum velocity in terms of meters per second. So this is all coming from the angular unit from 3A, basically, where we learn how to convert between angular velocity and regular velocity, and how to convert between angle and arc length. Okay, so I know that's a bit confusing, especially with the reuse of the variables. The next section, though, it's also still in 15.5, but this is really important if any of you are doing the locomotion part of the group project, which is how do we look at a pendulum system that's not just a mass on a string, but that is actually a solid object swinging back and forth. So that could be a stick, that could be a circle, any sort of lopsided solid object that has a mass that we let swing and oscillate. It'll look and act a lot like a pendulum, but it will have a slightly different formula. So instead of omega being root G over L, now we have root mg L over I. Okay, so we can talk about those components here, but the mg, this is just the weight of our solid object. And then the L, it's not the length of the object. This is very confusing. It's the length from where we're rotating, from the pivot point to the center of mass. So that's why they use a lowercase l here instead of a capital L. So capital L would be the length of this whole object. This lowercase l, you could imagine your arm, for example, is a pendulum if you let it just kind of hang free. And so, your arm has a total length, but instead you could think, where is the center of mass of my arm? So where would it balance? Roughly halfway. And so the length from my shoulder to that center of mass, that's this lowercase l. just to clarify. And then the I here is the moment of inertia of that type of object. And so I give you a table in the slides for the moments of inertia of all sorts of objects. The most common one that you'll encounter is this one down here. So just to write it in a larger font, for a solid stick, basically, that you're rotating around one end, the moment of inertia is 1/3 ml squared. This L is the whole length of the stick. And so I'm not sure, okay, I do give you some practice here. So, but basically we'll just plug this moment of inertia into this square root and be able to get our omega. And then everything else will be the same as the pendulum or the same as the mass on a spring in terms of it'll be, you know, a cosine omega t plus phi. This simple harmonic equation shows up over and over again. It's just the details, the things like the angular frequency that change based on the particulars of the system. Okay, so in this example, a student measures her leg length from hip to heel and finds it to be 0.9 meters. What is the frequency of the pendulum motion of the student's leg? What's the period? So we know the frequency is going to be 2 pi omega, and the period is going to be 1 over the frequency. So basically what they're asking us to do is to calculate omega. And we have our formula here. It's root mg little l over I. And for a leg, you can look at the pictures actually and see that it's the one I've circled. That's going to be the one that we see the most in biomechanics, which is 1/3 ml squared. Okay, and so we can plug that in and we get that omega. You can see the m is going to cancel. And so we just have g little l. But for a leg, if it's, you know, if this is our leg, if it's a uniform density, then the center of mass is just going to be halfway. So our little l is just going to be big L over 2. So we have big L over 2 over 1/3 big L squared. And then one of these factors of L is going to cancel. And we get square root of G over 2 times 3 is 6 L. Okay, so you can see if we had just imagined that this was a normal mass on the end of a string, we would have had a root G over L. But because we are thinking about the fact that the whole leg has a weight and it's, you know, an even distribution of weight, so it's not something we can ignore, we get an extra factor of 1 over root 6. Okay, so 1 over root 6 is smaller than 1. So that tells us that the frequency is going to be slower. So our leg oscillates more slowly than if all of the mass was where our foot was. And we just had like a weird puppet leg with a string instead of flesh. Okay, so now we can just plug in. We know G is 9.8, and we know that our leg length is 0.9 meters. So give me 1 second here. I forgot to do this step in my notes. So I get 1.35 radians per second. And now I can just plug that in. So 2 pi times that for the, I wrote this formula the wrong way, huh? The frequency is omega over 2 pi because omega is radians per second. We want cycles per second, so we need to cancel the radians. So if we do 1 over 2 pi times what we just got, that 1.35, we get a frequency 0.64 hertz. That's one of our answers. And then we can just invert that and get a period of 1.6 seconds. So this tells you that when you're naturally walking, you would expect your most comfortable walking pace to be about the same as the natural period of your leg. And so you should expect a normal full step to take 1.6 seconds, like this whole cycle. Yeah.
Well, when you came to the L's up there, I feel like it should be 3/2 GL instead of 3/2 times G over L.
You're right. You're right. It should have been. Thank you. Thank you. This should have been 3/2. Thank you so much. So if we do that instead, let's see here. Yeah, so the other parts of this should be correct because I did them ahead of time. But this should be 4.04 radians per second. Thank you for noticing that. Okay, so were there any other, thank you always for correcting me. I really do appreciate it. Were there any other questions or comments on this one? Okay, good. So then 15.6, we're not going to get too much into the weeds with this, but section 15.6 is on damped oscillations. So you may have noticed in real life, springs don't oscillate forever and pendula don't swing forever. They tend to slow down over time, right? So we might have a pendulum that swings like this. And then if you look at it a little bit later, it's moving back and forth in a smaller region, and then eventually it's stopped. Or similarly, the shocks in your car, when you drive over a bump, they're going to oscillate for a little bit. You might feel your car shaking depending on how things are tuned, but over time, that'll dissipate. And the reason for that is friction. And even though the friction in these systems is really complex, we can think of it very similarly to the case of laminar flow. So remember the case where you have a low Reynolds number, you'll have a friction force proportional to the velocity to the first power. And so that's typically the type of friction force that people will look at when thinking about oscillations. It also just makes the math convenient. And having a different force doesn't change the actual observables very much. So that's why they use this one. So if you use this friction force and solve the differential equation, then instead of just a cosine omega t plus phi, you get this extra bit here. So everything else is the same, but you get an extra little bit. Well, everything else is similar. Let me mention that in a moment, but you get an extra little bit, which is this decaying exponential. So this is a function that if we plotted it, it would look something like this. And so what this is telling you is that your amplitude, so your amplitude as a function of time versus time, is going to look something like this. At first, it's going to be a value of a, but then as this exponential decays, your amplitude is going to get smaller and smaller, which is exactly what you observe, right? If you let a mass on a spring oscillate in the real world, friction is going to slow it down, and over time, that amplitude is going to get smaller and smaller until eventually it basically stops. This formula, it'll actually never stop because it's a horizontal asymptote. But when things get small enough in the real world, they're able to actually fully dissipate their energy. So that's one adjustment. The other adjustment is that your omega is no longer just root k over m. It has this extra junk in it, right? This b is coming from the friction force. So your omega changes slightly. And importantly, because of the minus sign, it decreases slightly. So as a result, you're going to oscillate with a lower and lower frequency, which means that you're going to be moving, slightly more slowly, effectively, right? Remember that your maximum speed is something like a times omega. So that's going to look slower and slower. And that's exactly what we see. As the mass slows down, not only is its amplitude getting smaller, but because the maximum speed is a times omega, and both of those are small, the net result is even smaller. And so this blue curve actually shows you what the position versus time graph looks like. And you can see that it's just a cosine function. So this cosine part is the oscillation bit. And then this exponential part, we call this an envelope, because it's this dashed line. And in the same way that you put a letter in an envelope and it kind of constrains its shape, you put a cosine in a decaying exponential envelope and it constrains its shape. So that envelope is telling you how the amplitude changes over time due to the fact that there's friction in this system. So there's friction in the system stealing the energy, which means that you can't oscillate quite so far. And importantly, what we can do, instead of writing e to the minus bt over 2m, it's convenient to define this thing tau. So this is the Greek letter tau, which we call a time constant. And I know it's a lot to get into now, but you're going to see time constants rear their ugly heads again in 3C, if you haven't already, because when you discharge a capacitor, the amount of charge it has in it, if these words don't mean anything to you, that's okay. But when you discharge a capacitor, it follows a decaying exponential as well. And similarly with inductors and such. So you'll see these again. But basically what it's telling you is that if the time that's passed is of the order the time constant, then you'll have e to the -1, right? If the time that's passed in your system equals the time constant, you'll have e to the -1. E to the -1 is, I think I have it on the next one, is about 37% of the initial value. So when one time constant has gone by, so this time is tau, the system will have decayed to 37% of its original amplitude. When the second one's gone by, it'll have decayed to 13%. So each time a time constant goes by, in physics, we call this an e-fold, because we've decreased the amplitude by a factor of 1 over e, right? So after one time constant, the amplitude is a over e. After 2, it's a over e squared. So this is when t is 2 tau. This is when t is tau. When t is 3 tau, it'll be a over e cubed. So each time constant that ticks by decreases the amplitude by a factor of 1 over e. And so that's just a way of figuring out roughly how long this spring system will take to stop. So if you want a rough time for like how long it takes for a significant amount of energy to be dissipated, you'll just have to calculate 2m over b. And we would always tell you what b is. In the general system, it's a very hard thing to measure, but either we would tell you the time constant and ask you to calculate b, or we would tell you b and ask you to get the time constant. Okay. So if you're confused about this, I encourage you to rewatch this part or to look at section 15.6 in the book. It really goes in a lot of detail on these damped oscillations. And so then just to show you what this looks like, if your b is 0, that's what we've been talking about so far. So if your b is 0, your amplitude just stays constant. Your energy is conserved forever. If you have a small b, then your amplitude will slowly decrease. So these are the envelopes. These are this green curve, basically, just plotted on their own. And if as the b gets bigger and bigger, you get a faster and faster reduction in amplitude and therefore a faster reduction in energy. You're turning that energy into heat, which is what friction does. So, if I wanted to be really mean, I could give you a problem with a damped oscillator and calorimetry combined, where whatever energy the oscillator loses goes into maybe melting some ice or heating it up or something. You have the tools to solve that sort of thing, but I don't know. I'm not sure if I'm that mean yet. But anyways, so in the last couple minutes, we can try to get through the last few slides. So you might wonder what happens if I, instead of taking energy away from an oscillator, if I give an oscillator energy. We call that a driven oscillator. So driving an oscillator, a great example of this is little kids on a swing. So if you're pushing a kid on a swing, you're giving energy to a pendulum. And so you can, even though there's friction, you can cause that kid to swing forever. And in fact, the kid can change the length of their legs, which is changing the length of the pendulum. And by doing that at a regular interval, so periodically, they undergo what's called parametric resonance. and are able to drive themselves in the swing, which is really magical actually. And the physics behind that is quite tricky. But all I expect you to know, which is something that you can see in these images. So the x-axis here is how quickly I push. So imagine there's a kid on a swing in front of me. I could push them like 1,000 times a second, and they would just say, ow, why are you doing this? That's really mean. And they wouldn't actually swing very high. So if you push the child too many times, you're actually going to cause some cancellation. And even though you're giving them a lot of energy, it's not going to be good for pushing them. So that's what happens out here. So if you push, so this x-axis is how many times a second I'm pushing, the frequency of my pushes. If I push them too many times a second, it won't work out. However, if they're swinging back and forth and I push them really slowly, then a lot of the time while I'm pushing them, they're going to kind of hit my hands and run into me. So that's also not going to work. So if I push them too slowly, then they also won't have a lot of fun. But if I push them just right, then what you can see is that I increase the amplitude tremendously. So if as they come back to me, I push them, and as they come back to me, I push them. So whatever that frequency is, that will be what we call a resonant driving frequency. Okay, so that's the driving frequency where you actually are able to give them energy in such a way that they will oscillate to a higher and higher angle. And so the idea of resonance is that for each system, the system will have a natural frequency, right? For a pendulum, that's root G over L. For a mass on a spring, that's root K over M. And when you're trying to give energy to something, you want to push it at that natural frequency. If you're thinking about something like a building vibrating, you actually want to make sure that you don't oscillate it at that natural frequency, because you don't want to give it increasing amplitude and increasing energy. So anyways, we're basically done. We'll be moving on to traveling waves tomorrow, and that's where I'll leave it for now.